I think we should get started. So it is actually a pleasure today to have Willy Williams-Jones here to give the department seminar from McGill University. Willy is an ore deposits geologist. He has made innumerable contributions to the science of ore deposits. He's shifted paradigms again and again in terms of how we understand how different ore deposits form. His contributions range from field-based studies to experimental work and quantitative thermodynamic modeling. And so when he doesn't have the thermodynamic data, he goes in the lab and does the measurements. And so he's the full gamut in terms of his approach to things. Not only has he made huge contributions to the science of ore deposits, but he's also been, I think, just an incredible level of contribution to the communication of science as well as education. So he's, I think there are many classes or cohorts that have gone through McGill that have been trained by him and have gone on to populate campuses and corporate offices throughout Canada and the world. He was a person who taught me introduction to geology. That's why I'm really standing here today as a geologist, so thank you very much.
He was a great student, by the way.
So background, he's from, did his initial training in South Africa, came to Canada and did his PhD at Queen's University on metamorphic petrology, studying the contact oil of Mount Royal, and has moved into the ore deposits since then. He's been at McGill since 1977, he told me this morning. So that's a while. He's still an active, he has the largest research group in the department there, and still actively teaches courses as well. Well, you can, he studies all different kinds of deposits, from magmatic to hydrothermal, published tons of papers, and he's also received numerous accolades. He's the Geological Association of Canada, the Logan Medal, which is their highest award. He's also the recipient of the Penrose Gold Medal.
I think we've had enough of this
from
now.
SEG,
Enough.
and also one other thing, and that is that the Royal Society gives out medals for science, but one of the medals he received was actually for science communication and education, and that was the Miller Medal. And so I think that is one of the things that great scientists can also be great educators. Okay, so with that, I will give you Willy Jones medals, vapors, and volcanoes. Thank you.
Thank you. Well, I think that James overdid it a little bit there. What I'd like to do is make this interactive, so feel free to just interrupt me as we go along. The first part is going to be somewhat historical. I really want to set a context. It goes way back. But dig in. I really want you people to understand where I'm coming from. This is something that I've been playing with for the last 20 years, so quite a while. I've actually moved on to other things. I'd love to tell you about carbonatites, which is my latest thing. But anyway, the picture that you see there is actually from a volcano that we worked on about 10 years ago. A really cool volcano. That is the image of the volcanic dome at night, at midnight. Magnificent. What's going on there? Talk to me, people. What's going on? What are you seeing?
Vapors.
Yeah, so you're seeing vapors. What you're actually seeing is elemental sulfur that is actually ignited and giving you those beautiful blue flames. So you're going to see a little later a picture of a dome, a volcanic dome sitting down in a crater. During the daylight, it looks kind of ordinary, kind of dangerous, exciting, but at nighttime, it's just magnificent. So a number of years ago, I actually took a group of students down at midnight and blew them away with images like that. Anyway, so what I want to do today is I want to talk about, as you can see, metals. I'm into ore deposits. I really want to understand how metals are concentrated in the Earth's crust. I'm going to try and convince you that vapors are really, really important. We kind of think people who look at ore deposits say, oh, it's hydrothermal liquids, hot water, and we need this hot water to transport metals, and there's no goddamn way that you can transport metals in the vapor phase. By the end of this lecture, I really want to convince you that yes, you can. And I'll convince Marcus over there that his porphyry copper deposits are in fact, for the most part, created by vapors, not hydrothermal liquids. Okay, it's not a new idea. It's actually an old idea. You can count the number of years. It goes back to the 1500s. You should all have heard of Agricola. Who hasn't heard of Agricola? Okay, you can translate it. George Bauer. So, a German scientist in those days, Agricola, the farmer, and what he was farming was obviously metals. And if you look at what he says is, metal exhalations are drawn up from the depths, and being fumes, they rise and pass into valence. So where he was at was the whole idea that yes, when we look at ore deposits, back in the 1500s, obviously they came from fumes rising to the surface into fractures in the earth. So not a new idea. Fast forward, and now you're getting some heavy-duty science. You've got this guy, Sir Humphrey Davy. Have you all heard of him? You heard of the Davy lamp? Canaries, mines. Okay, so this guy actually was on Vesuvius in 1820, just at the time of an important eruption. And if you actually read what he said, and he published this in the Philosophical Transactions, on the 6th of January, I collected sublimations. What he means is, I've collected deposits from a vapor, because it was the volcanic gases. One specimen with large saline crystals, so you know that is salt, with a slight tint of purple, proved to be the common salt, with a minute portion of muriate of cobalt. What the hell is muriate of cobalt? Talk to me. What's muriate of cobalt?
Is it muriatic extract?
Muriatic acid, hydrochloric acid. So chloride. What we were really looking at was cobalt chloride. And carry on with the sentence, the same story with copper. So what he was actually seeing was metals being transported by vapors and deposited. So we knew that back in the 1820s. You look at this guy, Auguste Dobré, a really great French scientist, again, 19th century scientist. He was actually interested in the Cornish tin fields. And of course, what was in vogue then was the whole idea that we transport metals in the vapor phase. So what he did with his experiments is he actually took tin chloride. You probably all know that tin can be in the 2+ state or the 4+ state. Anyway, tin chloride, so it's obviously in the 4+ state over here, actually is a gas. It's a vapor at 114, 15 degrees centigrade. So what he did was a really cool experiment. He simply took tin chloride as a gas, he ran steam through it, and he actually precipitated the ore mineral that you find at Cornwall, cassiterite, tin oxide. So people back then, I think one of our errors these days is we forget the contributions of people like that. How many people have actually heard that name here? Not one of you. That's telling us something. We've got this kind of habit, oh, if it was published 5 years ago, it's sort of out of date. Every science advances. But we forget about the major contributions that were made a long time ago. And I think it's really helpful to go back and read the old literature. Okay, so 1800s, the vapors are doing the job. Then we get the changing of the tide. We get Valdemar Lindgren. And anyone who studies ore deposits geology knows that this guy was the father of economic geology. And if you read what he says, in ore deposits there are vast quantities of non-volatile metal, particularly silica. Basically what he said is there's no way that you can transport these metals in vapors because we see these quartz veins. Well, you can't transport silica in a vapor, so that's pretty well the end of the story. He was followed by this guy, Louis Graton, who actually did his PhD at McGill. And if you just read at the bottom, it is improbable, so he didn't say impossible, but he said improbable that an important gas phase exists in a normal magma. There's no way we dissolve an aqueous fluid, or water if you like, into a magma. Well, we know that's not true anymore. And you carry on, and even if it did exist, it would be so inferior to an aqueous liquid that we can basically blow it off. And so in the start of, basically in the late 1890s, beginning of the 20th century, that was the end of the whole idea of vapor transport, killed by these two individuals. One from McGill. Okay, again, a little bit of history. This guy, George Morey, you can see him in the lab there. He and people like Bowen, and you've all heard of Bowen and Bowen's reaction series, Fenner, they were working at the Geophysical Lab, the Carnegie Institute in the US, and they were defending this whole idea of vapor transport. And you can actually see Morey here was actually running experiments in the 1920s, as I recall, 1920s, 1930s, actually looking at, can we transport metals in the vapor? And he was particularly interested in attacking Lindgren in terms of silica. And what he actually noticed, approximately 50 grams of quartz had been deposited at the top of the bomb. I won't go into the details, but the message is, yes, we can transport silica in the vapor phase. So you can see that it was a huge debate. And then it all came to an end. Krauskopf. How many people know the name Krauskopf here? Famous geochemist from Stanford, great geochemist. He did a bunch of calculations. He said the very low volatilities of copper, silver, etc. show that the simple vapor transport model basically can't work. So write it off, and that really was the last nail in the coffin of the idea that we could actually make ore deposits with aqueous vapors. And so what he did is he calculated the vapor pressures of these different metals, and you can see he actually took them as chlorides, and you can look at these numbers here, and you're saying, well, I can put 10 to the minus 17 into solution, or 10 to the minus 3. Well, we can think of a ppm as 10 to the minus 6, or even a ppb as 10 to the minus 9. You look at those numbers, it's game over. There's no way you can transport metals in the aqueous vapor. But now you start to look, and this diagram, in fact, I saw it on Marcus's poster this morning. So what I really want you to focus on, this could be a magmatic system, or if you like, a porphyry system. You've got magma here, you've got fluids coming out at the tops of volcanoes. But I want you to look at this phase diagram here. If we actually look at the composition of that fluid that is being exsolved, notice that it is hitting the vapor side. So the critical curve would go right through here. That side would be water, this side would be vapor, and clearly, in terms of this picture that I'm trying to push, if you buy the idea that these fluids that are exsolved probably only contain maybe 5 to 10 weight percent NaCl, then there's a good probability that you're in fact going to exsolve a low density fluid, a low density supercritical fluid that would ultimately become vapor. In other words, that fluid, supercritical, would come up, it would hit that solvus, and most of it would be vapor, and it would condense a small amount of liquid. We can debate this back and forth. It obviously depends on the level of emplacement of the magma. If the magma is deep, well then obviously you're going to be on the other side, and you're going to exsolve a supercritical fluid with liquid-like density. But these porphyry systems are typically in place to fairly shallow depths, a few kilometers, 2-3 kilometers. And at those depths, you're going to exsolve a low-density supercritical fluid. And in fact, if you look at fluid inclusion studies of many porphyry systems, what you find is they're dominated by the vapor-rich inclusions. Yet, we persisted. We said, well, this can't transport the stuff in the vapor, so we'll do it with a liquid, or we'll get a liquid from somewhere else. We couldn't accept the idea that the vapor could transport the metals. And then you actually start to look around. Go to volcanoes. Go to so-called epithermal systems. And what do you notice? You notice rocks like this. This is simply a volcanic. It could be a rhyolite. It's literally lost everything. All you've got left is a holy rock, not so holy, but you know where I'm coming from, that is just pure silica. So you've literally leached everything out. To do that, you've got to have a very acidic fluid. How do you get an acidic fluid? Well, if you've got a vapor, all of those acidifying components are going to go into the vapor. Where's the sulfur going? SO2. It's going into the vapor. Combine it with water. You've got sulfuric acid. Chlorine going in there. You get hydrochloric acid, and so on. So there's no problem. You're going to get an acidic fluid if you have vapors. And there's another example of, again, rocks that have been altered, and the mineral alunite is also diagnostic of fairly low hydrogen ion concentration or acidity, high acidity. This guy was key. So 40 years after it had been basically debunked by Krauskopf, Chris Heinrich came along at ETH, started analyzing fluid inclusions, and he came up with some huge numbers in terms of the concentrations of metals in vapor-rich fluid inclusions. And so he had the first evidence that perhaps vapors could be transporting the metals. You'll see in the next slide that we ran into a little bit of a problem, but it was pretty exciting. At about the same time, my group started to do experiments. We started to do experiments to actually look at the solubility of metals in aqueous vapors, and I'll talk about those a little later. But Chris ran into a problem. One of his students, interestingly, with his student, so a former student of Chris Heinrich, worked with one of his students and said, this is actually an artifact. What they actually showed is you could actually produce fluid inclusions with chalcopyrite crystals in them, in other words, vapor-rich fluid inclusions, by diffusion. So all you needed is a situation if your environment had very high pH, in other words, very low acidity, then you'd have hydrogen ions moving out of your fluid, and you'd have copper ions moving into your fluid. And so he actually reproduced this, started with a fluid inclusion that had no copper in it, or no chalcopyrite, and produced that. It was interesting. As soon as that paper came out, the community said, it's all bullshit. Sorry, I tend to swear from time to time. Anyway, the point is the community basically rejected the whole idea that vapors could transport metals based on that. Okay, so let's go to volcanoes. So we've done quite a bit of work looking at active volcanoes. And this one is called Kawah Ijen. I'm going to spend a few slides on it. It's in Indonesia. It's a wild volcano. It's super cool, easy to get to. It's the picture that I showed you right at the beginning. What are we looking at? We're right in the crater. All of these rocks, rhyolites, dacites, and so on, they're all altered. You can see if you go up and you were to actually hammer at this, it's all clay minerals, and the darker color there is actually pyrite. So that's a crater there, and we're seeing lots of evidence of alteration. How could it be? Well, you're degassing. You're degassing, you're creating a very, very acidic condensate. Have a look at this. Here is a pillow lava. That pillow lava is running about 90% silica. What has happened? That pillow was created, probably from an andesite, and literally you've removed everything from it, leaving behind some silica. So if you have any doubts, I think that go down into that crater and you'll be pretty well convinced that there's been a hell of a lot of alteration going on, and literally you have leached out stuff, you've altered it, and you've done all of this stuff with a fluid that had to be a vapor. That's what you're degassing. If you don't believe it, well, just go and have a look. You have a dome there. That dome is degassing at the present time. We've got a lake down there. We measured the pH of the lake. That pH, I think, was what we get about half, 0.5. That's pretty acid. In fact, a little anecdote there. My son, who's a volcanologist, and I were actually on that dome, and some bloody tourists came down. Some French tourists came down, brought in with a guide, and this young girl was about to dive into this lake.
Oh.
And my son and I screamed. You know, I mean, we were sitting there trying to do the sampling. We screamed like hell because if she'd gone in, she would have lost her eyes at the very least, because she was diving into a lake with a pH of 0.5. Anyway, people do strange things. So here we are, busy sampling the gases. That's yours truly over there. Obviously, we're wearing gas masks. We've got we inserted a tube there to see if we could get sublimates, and we did. Most of it is sulfur, but you actually get some metal sublimating. That particular one, we measured at about 600 degrees centigrade, and the condensed gas, or the condensed vapor, came out with a pH of minus 0.6. You don't often see pHs on the negative scale. So we're dealing with a highly acidic environment, and now you understand why those rocks are so altered. They're being subjected to gases that have condensed and on a fairly large scale. So the locals actually put these ceramic pipes, you can see the ceramic pipes, they put the pipes into the fumaroles, and the interesting thing about this volcano, it's obviously degassing a lot of sulfur. But you think about sulfur, sulfur can be either in the H2S form, in other words, sulfur is -2, reduced. It could be highly oxidized as SO2, then the sulfur's in the +6 state, or it can be intermediate. If it's intermediate, it's elemental sulfur. So in fact, that volcano, as I showed you with the very first slide, is actually emitting elemental sulfur, and that elemental sulfur is catching, well, basically igniting. So all you've got to do is increase the oxygen fugacity to some critical level, and you emit elemental sulfur. It's a pain in the butt being on that volcano, sampling this stuff, because every hair on your body gets coated with elemental sulfur. Could you imagine it? You come out with yellow hair at the end of it. Anyway, what the locals do is they actually trap the gas. It condenses. As you cool it down, it turns to liquid. The liquid comes down. You make a pool of native sulfur at the bottom, and wait minutes, literally. It quickly cools, hardens, and then these poor guys end up breaking up the sulfur into pieces, and those pieces they put in baskets. They then climb 150 meters vertically with 70 to 90 kilograms of sulfur on their backs. I tried to pick up one of these. I couldn't even lift the damn thing, and these younger guys were actually just literally walking out of the volcano. Just unbelievable. What do you think the life expectancy is? They are in and out of highly acidic gases. Life expectancy under 50. It's just pretty awful. Anyway, one of the things that we did, one of my master's students mapped in the crater, and so what we did is we mapped in yellow zones of ultra high acidity where you'll see cristobalite. This is really just vuggy silica where you've just removed everything out. And you'll see a beautiful zonation which represents a pH zonation. You go from the vuggy silica through into this mineral alunite, which I talked about earlier, and then eventually into kaolinite. And what we have is this dome, which you can see over there, has been moving around with time, creating that alteration. So there's absolutely no doubt that we're creating the alteration that we see for ore deposits, people, associated with epithermal deposits. So if I use the term high sulfidation epithermal deposit, if you've taken an ore deposits course, that is a type of gold deposit, gold-silver deposit, that you see associated with that. And we're seeing evidence of that. We can actually see veins over here. This vein has got the mineral alunite in it. Right next to it, it's got pyrite in it. If we go and start to analyze it, we actually see that the pyrite contains gold. It contains gold and it contains silver. It's running about 1 ppm silver. It's running, maximum about 0.1, maximum close to 1 ppm gold. You'll say, well, that's really low. Well, it's actually pretty bloody high when you think this is on the surface. This is not at depth. And already we're getting these concentrations in this pyrite, which we know is coming from this condensed volcanic gas. So we're starting to build a case that this metal may be transported by that. We then move north in Indonesia, go to a place called Sangier, and it's an island. It's an island that's eroding incredibly rapidly. They get 6 meters of rain every year, so you can imagine the rate at which this is eroding. You've got the active volcano right over there. The volcanic center has simply been moving around, and we're looking at 2 deposits there, which are probably less than 10,000 years old. That simply represents the erosion of the volcano. So we've gone from 1,300 meters to less than 100 meters above sea level. We are eroding at an incredible rate, and so that gives us an opportunity to actually look within the volcano to see what's going on. And what we can see in detail is we'll see the same pyrite. That rock looks exactly what we saw at Kawahijan volcano, except that here you do have an economic gold deposit running about 1 gram per ton. Not super high grade, but it looks exactly the same as what we formed in that volcano. Okay, so what did Kraskov ignore? What he ignored was 2 things, and it wasn't his fault, the work hadn't been done there. He ignored the fact that we can form metal complexes, that we can actually bind gold or silver with a ligand, bind it with an anion to make a complex species that could dissolve. The other thing that he ignored was the nature of vapor. When we talk about water vapor, what do we really mean? What we really mean is that it's not just individual water particles or water molecules. We'll get clusters of water molecules. You might have a cluster here, another cluster there, and then individual water molecules and so on. And so what you can do is you can hydrate this. And so here is your complex species, and now what you've done is you've hydrated it. That would be the gold, the gold in that complex. And you'll notice the gold which would be positively charged, is bound to the negative side of a water molecule. So you're using the same idea of solubility, that basically we hydrate these metal ions, except in the vapor phase, we play with clusters. And so here is a molecular dynamic simulation that we've done. I didn't do the work, but one of my postdocs at the time, she did the simulation, and what she's done is she's actually said, well, how does this molecule actually look? And so we've got a copper bonded with a chloride, and so, copper bonded with a chloride over here. That's the copper, that's the chloride. It's simply a simulation, it's a mathematical simulation, but you can see that if I look at the water molecule, the oxygen is linked to the copper, and vaguely the positive hydrogen is pointing towards the chloride. So that's what the molecule might look like. And so to summarize, that's the sort of picture that you're actually going to get. You're going to get individual water molecules in a vapor, and then you'll get clusters. And then you can take that next step and you can say, if I've got clusters, well, if I increased the pressure on that vapor, then I'd have a larger number of clusters, and therefore I should get increased solubility. Have you all understood every damn thing I've said for the last little while? You're really quiet. You need to talk to me.
Marcos, help us out here.
Okay, I'll roll along, but please interrupt me when you want.
I was curious about, you mentioned the clays earlier on.
Yeah.
So what type of clays were they? If I can-
Kaolinite.
Okay, oh, really?
So
That's the heaviest of the clay minerals. Why do you think that's?
well, it depends on how you look at it, but if I looked at, let's say I wrote reactions between kaolinite, muscovite, and K-feldspar, I can actually order them in terms of pH. So my K-feldspar will represent high pH, my muscovite will represent intermediate pH, and my kaolinite will represent lower pH. So that's where we're coming from with that.
Where do you draw the line between clusters of water molecules and condensed liquid?
Okay, really good question. It's a fuzzy line, but it's actually fuzzy, but it's actually fairly sharp. We can actually measure the oxygen fugacity at which we hit that boundary, and it's very, very sharp. You'll see in the next slide, I think you'll start to get a sense of it. Let me just show this next slide. So what we're looking at here is the solubility of silver in water vapor. And so you can see that as we increase the fugacity of water, we are gradually increasing the solubility of the silver chloride. If we kept going about over here, at that water fugacity, we would actually get to liquid water. So there's really a continuum. The solubility curve would go like that and then basically flatten out at a certain critical point. So it is kind of arbitrary because what you're really saying is pure liquid water, every water molecule is bonded to every other water molecule by hydrogen bonding. Anything less than that, and it is a high density vapor or a low density vapor. But trying to determine that actual point is tricky. What I want you to get out of this is we're actually making different species. So over here we've got silver chloride with one water molecule. Here we've got silver chloride with 8 water molecules. How are we doing it? Dead easy. All we're really doing is looking at the slope of the curve. We're simply finding the derivative of that curve, and that derivative is going to actually tell us the hydration number of the species. And of course we've got the concentration. From that we can actually extract a lot of thermodynamic data. If you took a basic thermodynamic course, you'd write this reaction and be the silver chloride plus so many water molecules making that. You could find the log K of that. You would say log K is equal to minus Gibbs free energy change over RT. This would be your basic thermodynamic expression. And we can take it a step further. We can actually do the calculation. So here we're actually looking at the Gibbs free energy of a particular species. In this particular case it is silver chloride with 2 water molecules. And what you see is there is a linear relationship as a function of reciprocal temperature. And so the temperatures are up here. So the high temperature over there, low temperature there, and you can see your delta G changing. And the fact that it's linear is cool because it allows us to actually model to temperatures well beyond the temperatures of our experiments. Okay, and so this is what we did. And so now what you'll see, you'll actually look at the solubility of silver in parts per million, and you get big numbers. In fact, the silver mines in Mexico, if you've ever been to Guanajuato in Mexico, you see a bunch of silver mines there. Their grades are similar to what we're actually able to dissolve in a vapor. So you're starting to get a sense now that vapors can, in fact, transport a lot of metal. You'll also notice that it reaches a peak and then drops off. And what you've got is you've got a competition. Increase the temperature and the damn molecules fly apart, right? So increasing temperature is compensated by increasing pressure, which pushes for hydration. And so you effectively reach a point, a maximum, after which temperature takes over, and that's the end of the game. So the solubility max is somewhere around 475 degrees, but it's pretty high. Okay, we can do the same thing. I'm not going to bore you with a lot of this, but you can play the same thing with copper. We've done that with copper. Hope you like my clown. The whole idea of the clown is that if we think about what a vapor is, and we think about that whole idea of hydration, what you've actually done is imagine yourself in the circus. You're a clown, you've got all of these big hydrogen balloons, a little risky, you've got them in a bunch, you're going to get lifted off the floor. Well, the same damn thing is happening here. What you're really saying is, I have bound my little silver chloride and my copper chloride to a bunch of water molecules, and I'm lifted into the vapor. So I hope you get that analogy, because that's what I want to sell. Okay, anyway, you can see it's the same story. You want to have a look at the solubilities, and we've done the calculation in equilibrium with chalcopyrite, which is a common ore mineral in porphyry copper deposits. And look at the numbers there. We're getting 3,500 parts per million. That's big. In fact, if you actually look at fluid inclusion studies, they get similar sorts of numbers. So there's absolutely no doubt that that vapor coming off the magma is able to actually transport considerable quantities of metal. I'll give you a last example with gold. Here I'm showing you an extra graph. What we wanted to find out here is, what is the nature of the complex? And if you have a look at this, what we've done is we've varied the fugacity of hydrochloric acid. Looking at the concentration of the metal, you get a slope close to 1. So what you can say is that one gold atom will combine with one chlorine atom to make an AuCl complex. And then the other you've seen. I don't know what the hell happened here. Forget that. Okay, so if I take this a step further, we can actually calculate things as a function of depth. And what you'll notice is a Victor density of the water vapor of 0.2. That is a vapor. We've also got a number of 0.05, and 0.35 or 0.38 is your critical density. So what you can see is in each one of those, you reach a solubility maximum, above which it drops off. And if you look at the numbers, we're over 10 ppm in solution in the vapor. Okay, so let's now go to what we can see in nature. So what we've got plotted here is simply pressure against temperature, and this would be the water curve over here, and you can see isocores. Do you know the word isocore? Simply a line of constant density. So you've got different lines of different density. Your critical density is 0.3 something or other. And what I want you to notice is all your fluid inclusion data, or most of it, is actually in the vapor field rather than in the liquid field. So if we're up here, we would be in liquid. Down there, we'd be in vapor. Okay, here's some more data again from fluid inclusions. And what we're looking at is temperatures of, we're looking at temperature, and then we're looking at concentrations. One of gold, and the other, copper, and the other of gold. And what I want you to see is the fluid inclusion data shows that you get to a max. And you see the same thing with gold here. You get to a solubility max, which is exactly what we saw in our experiments. So nature is vindicating, I think, our observations. Here we're taking, again, data from natural systems, and what we're looking at here is the copper-gold ratio of the ore deposit. So we're actually looking at the ore deposit, and we're plotting the copper-gold ratio versus the molybdenum silver ratio. And so you'll see a bunch of dots over here. So these ones, Grossberg over here, is a gold-rich porphyry, and then others will be having much higher concentrations of molybdenum. You can see over here, if I look at Chuquicamata, which I'm sure Marcus has visited many times, El Teniente in Chile, you can see that these are rich. They're much richer in copper and much richer in molybdenum, and these ones are much poorer in copper, in other words gold rich, and of course low in molybdenum. So the conventional wisdom would be they have different sources. People have argued for years that they have to have different sources because the metal ratios are different. So what we did is we actually took all of our experimental data and we said, let's actually model a system. So what we did there is we plotted all the data, and these lines here represent a modeling of our experimental data, and we modeled our experimental data in terms of sulfur. So we go from low sulfur to high sulfur there. We just basically said, let's go from 0 to 10%. Why? So the question for you, how much sulfur do you see in a volcanic gas? Reasonable question. The answer could be, very often you'll get up to about 4-5 weight percent. So high concentrations of sulfur in volcanic gases. In fluid inclusions, the numbers that have been measured are significantly low. I think the highest is about 1 point something weight percent. I'm sure Jacob over there could help us out on this. But the point that I'm going to make is, if we look at Grasberg over here as this gold-rich porphyry, one of the things that characterizes it is a very high sulfur content. So let's go back to our volcano. If we think about that volcano degassing, where's the sulfur go? It goes into the vapor. It goes in either as H2S or SO2, or even elemental sulfur, but it goes into the vapor. It's going to be way lower in the liquid. And so we see these high concentrations, and so just look at this pattern, look at it carefully, and then our modeling, and we had two models, one with fairly low chloride, and then low chloride, just 500 ppm, and then another with 0.3 weight percent chloride in our solution. So you've got these two curves, and you can see that, look at this dark green curve, both of them almost mimic the distribution of the grades. And we're just talking about the metal grades in these deposits. And so what we're trying to say is sulfur is one of the key components. Chloride is another one. But the sulfur is really, really important because it affects the complexation. Simply put, if I want to transport gold, I love sulfur. Gold will make very strong complexes with sulfur. Not true for copper. Copper would be much happier at these conditions as a chloride complex. And so as we go to high sulfur, what we're going to do is we're basically going to get down to Grasberg. And Grasberg, of all the systems that we looked at, has the highest sulfur content. So really what I'm trying to say is this whole idea that you can transport metals in vapors can be taken a step further. You can actually just model the data and actually explain the metal ratios because of the nature of the complexes that you actually form in these aqueous fluids. I have a final slide which got into the wrong place, but I will just find it again. And that's my final slide. So thank you. That's basically the conclusion. We really feel very strongly that low density fluids, in other words, either supercritical fluids or vapors, are responsible probably for the majority of porphyry copper deposits, porphyry molybdenum deposits, epithermal gold deposits. We're talking about ore deposits that represent a resource which is damn important to us. Porphyry copper deposits are probably the most important resource of copper, and we're submitting that these deposits were made by vapor and not by liquid, aqueous liquid, which has been the paradigm that's accepted up to the present time. And then we'll take a next step further, which is super arrogant of us. We're saying it's not an issue of source, because you go and read the literature and they say, oh well, it's rich in moly, so we've got to go and get it from magmas that are rich in moly. I'm saying no. We're saying no. think about the fluid chemistry, do the thermodynamics, do the modeling, and you can at least predict that you can do it with the chemistry of that fluid. So I'm not going to say that's right, but certainly that's what our modeling is showing us. And on that note, I'll shut up.
Okay, well, thanks, Willie. Our tradition is that we actually let our students ask the first questions in these seminars. So do you have any students, graduate or undergraduate, who would like to challenge Willie on any of these
I'd love to be
ideas?
challenged.
Or even
You've got to
ask?
debate these ideas. Yeah,
I
go
don't know
for it.
about a challenge, but do you think that there's any significance to carbonic fluids in metal transport?
Ah, huge question. All right, so what is the role of CO2 is basically what you're saying.
Or methane?
Or methane. So what you've got to do is you actually got to look at the molecule. If I look at CO2, CO2 is a linear molecule, and so it's a lousy solvent. So it's not going to be the CO2 in terms of complexation that's going to do it. If I look at methane, it's the same story. It's one carbon surrounded by those four hydrogens. The big beauty of the water molecule, it's a polar molecule. So the oxygen side is negatively charged. The hydrogen side is positively charged. That's why it's such a great solvent. But the CO2 is going to play other roles. It's going to, for example, change the dielectric constant of the fluid. So what is the dielectric constant? Anyone know what the dielectric constant? Go for it. You can take over.
I'm used to dielectric constant in terms of GPR, electron penetrating radar. Is it different?
Yeah, it's a little different.
Okay.
Okay, so what we're really looking at here is, if you could imagine, I'm showing a diagram, imagine I've got two plates here, and I'm going to have a potential between them. So I've got two plates, I've got a potential. I've got water molecules randomly orientated between those two plates. Up the current until they all line up, so that the positive end of the water molecule is pointing in the direction of the negative plate, and vice versa. So that is basically the dielectric constant. And it turns out, if you think about it for a moment, if the water is nicely organized as a liquid, every water molecule is bonded to every other water molecule, it's kind of well behaved, and the dielectric constant will be really high. It's going to be difficult to get all of those water molecules to be oriented, because they say, I love that next water molecule. I want to be bound to it. So the dielectric constant is really high for liquid water at 25 degrees centigrade. But if I increase the temperature, then I vibrate these molecules. I break that hydrogen bond, and the dielectric constant plummets. And so, in fact, in vapor, the dielectric constant is really, really incredibly low. And so solvation is much more difficult under those conditions. Does that sort of answer it? So it's really, as I increase temperature, we get more vibration, and the orientations of those molecules change. So it becomes easy to line them up with two plates. If they're all unbound from other water molecules, then you can line them up, and you get a low dielectric constant.
So, sorry, how does that refer to the carbonic vapors?
Sorry, how does that?
You said that the carbonic vapors might affect
Okay.
the dielectric.
So if the dielectric constant is high, water is a really good solvent, because it can organize itself. So it will organize the negative ends of the water molecules around a cation and the positive end around an anion. As you start to break that apart, what happens is you get complexation, because the chloride ion now can say, oh, I see that gold ion over there, and I will interact with it. The water hasn't prevented that interaction. And so what the carbon dioxide is doing is lowering the dielectric constant, and therefore promoting complexation, but it's not the solvent. Okay. Marcus.
We're all students. Willy.
Me too, I'm a
Okay,
student.
ladies, jump in there, so go ahead.
In many porphyry coppers, you notice that the mineralization coincides with times of fast uplift and erosion.
Correct.
And so you think that that has to do with the essentially the boiling of vapors at that moment?
Yeah, I think that this uplift is really key to the whole thing. We're obviously going to be, if we are down here, the water is nicely dissolved in the magma, right? So it's in no hurry to come out. You bring it up fast, and the solubility of the water is now way lower, and so the water is going to exsolve, but you're at high level, so how's it going to exsolve? It's going to exsolve as a supercritical fluid of low density. So I think the two are interrelated.
Which also will help the fracturing of the rock, right?
You're damn right. I mean, you bring it up like that, and you've got the explosive power of this expanding vapor.
Hydrofracturing.
Hydrofracturing, hydrovapor fracturing.
Hydrovapor fracturing. Well, they fracture with vapor too, with gas too.
That's right. I think there was a question at the back there.
You show these pyrites which have a lot of gold in one of the
Sorry, could you
slides.
repeat that?
You show these pyrites
Yeah,
which
yeah.
have a lot of gold, but what about the arsenic content there?
Ah, you raise an interesting thing. We've actually got a cool project going at the moment where we're actually trying to explain bonanza gold, kilograms of gold per ton. And it turns out that what happens is the charge on the surface of that pyrite crystal is really, really important. If I was transporting the metal as some sort of charge complex, if I was in the liquid phase, for example, I would say AuHS2 minus. That 2 minus will actually say, gee, I see a pyrite crystal over here. It's got arsenic in it. Its surface, because all sulfide minerals are semiconductors, its surface will have a positive charge. So you'll suck in, the pyrite will suck in those gold complexes and build up on the surface of the pyrite. Then you reduce it, and you can actually include the pyrite, the gold within the pyrite as it grows.
You mentioned silica earlier on.
Yeah.
Is there a role for vapor in forming quartz veins in sedimentary, low-grade metamorphic rocks, or are the temperatures too low for this kind of phenomenon?
The temperatures are, well, what temperature? You give me your temperature.
I don't know.
At low temperature, I mean, the issue ultimately is what is the phase of the fluid going to be? At low temperature, if it was a vapor, it would have condensed now to liquid and vapor, and that liquid will suck up the quartz. If I look at solubility of anything, if I've got a direct comparison between vapor and liquid, the liquid will have higher solubility, the metal will have higher solubility, or the silica will have higher solubility in the liquid than the coexisting vapor. So where I've been coming from today is the fact that these systems are dominated by vapor. It's not to try and say, and lots of people have confused us, we're never trying to say that the vapor is a better solvent than the liquid. What we're saying, if you've got 99% vapor and 1% liquid, don't look at the 1% liquid as transporting the metals. And it'll be the same for quartz. So in principle, yes, as Maury showed, we can transport silicon vapor. But under your conditions, I think it'd be the liquid.
So in a similar way, I've got the salt flow like we have here in Nova Scotia. That would probably be dominated by a liquid.
Sorry, repeat that?
The basalt
Oh,
flows
yeah.
of the
Well, okay,
magmatic
well,
province.
so I
we
mean,
have lots of agate, banded agate formed, and copper in the basalt.
that's right, and so then your question is going to be, when is all of that happening? You have the agates, when are they actually forming? So it's not clear to me what the timing is. You're going to have extrusion of a basalt. Maybe you can build up a pile of basalts, and maybe down at the bottom you could be exsolving some fluid, and in that case that fluid would be exsolving as a vapor. But it's a real problem in terms of the timing of all of this stuff.
Wouldn't it be near the cooling phase, and wouldn't the crystal sizes be dependent upon that rate of cooling?
Crystal size, I mean, that's a huge area. Crystals can be damn big and grow really quickly. All you got to do is go and see a pond in the morning, and you'll see ice crystals this long, and you know darn well that they've just formed in a few hours. I mean, it's a huge issue in the study of pegmatites right now, huge debate. Why do we get large crystals? And historically, people would say, oh, well, you get large crystals because magma cooled really slowly. Well, we all accept that you can, in fact, grow those large crystals quickly. And what it comes down to is the rate at which you can get the nutrients to the growing faces. And so if my liquid is low viscosity, then I've got no problem. So if I've got super low viscosity, I can move that material fairly rapidly. So it's complex. Yep.
John? Willie, I asked Jacob this, and so he said yes, but now I would like to hear.
You're pitting the two of us against each other, are you? Go for it.
I wonder if you or anybody has used isotopes of gold or silver to show that it had to be at a vapor state because the temperature of evaporation at that point matches the isotope ratio.
Hang on, I didn't say isotopes of gold. Gold is monoisotope.
Okay, well, I'll say something about
silicon and copper.
I'll say something about silver isotopes. We just, I guess last year, we published a paper looking at silver isotopes, but we're at the stage where we're only starting to get a handle on the fractionation as a function of temperature and the partitioning of these isotopes between phases. And so, to my knowledge, no one has taken it the next step and said, can we apply silver isotopes and actually address that question? So I don't know the answer to that, and I might have missed recent papers, but as I say, I don't think there's going to be much out there at the moment. That whole area, I mean, now we're getting isotopes on the periodic table, basically, and I think in the next 5 to 10 years, we're just going to get an explosion of information that we're going to be able to use, or new tools to actually interpret things like this. So we've got a long way to go. Yeah?
So it looks like that PT path will actually determine whether your supercritical fluid will end up as the liquid or
exactly.
the vapor.
It's your PT path.
And then, so does it mean that basically PT path can, so if you constrain PT path, then you can predict how high will be mineralization, because if your PT path will bring you to the vapor field, then you will have, from the same amount of water, you will have lots of media for transportation.
Yeah, but it does still come down to the debate over whether liquid is a better solvent than vapor. And I think we would all agree that liquid is the better solvent. It's really a question of which field we get into. So how do we solve that?
Yeah, that was my actually other question. So liquid is a better solvent, but from the same amount of water, we have way more vapor. So how does it balance each other? Is it still better to be in the liquid phase, or it's better to be in the vapor phase to be more efficient in forming the deposits? Or it pretty much cancels each other?
You ask a complex question. My feeling is that a smaller amount of liquid will be better than a larger amount of vapor. It's really just a question of the mass ratio between the two. And what I've been trying to argue is that in these porphyry epithermal systems, the mass ratio is such that vapor vastly outweighs the liquid, and that's the issue. Go for it, Jake.
So, I mean, we've looked at now in the literature barren and endowed granitoids, and we know that metals are kind of the same. There's not a big difference.
Exactly.
What are your thoughts about the competition between sulfur, water, halogens? So this is getting back to the magma endowment part. Is there any sweet spot in terms of magma composition that sets the stage for what you've been talking about?
Yeah, you ask a tough question. There has to be a sweet spot, but it's going to have to be dependent on the metal. So if you say, what would be the sweet spot for gold, I'm going to say really sulfur rich. If you say, what is the sweet spot for molybdenum, don't give a damn whether it's sulfur or chloride. In fact, my complex for molybdenum, we've just done finished some experimental work a few years ago, we don't think either of those play a role. What we actually think is that the dominant complex would be a molybdate, and in fact we think it would be a sodium hydrogen molybdate. So I think it really comes down to the fluid chemistry and the nature of the complexes that we form. And so I think we need to do a lot more of this work.
So just as a follow-up to that, on your, it was the moly, silver, gold, copper diagram?
Yep.
Where you're putting forward the idea that it doesn't matter what or originally thought this was a source thing.
Yeah.
But it does require differences in the water to sulfur ratio.
It does,
to
yeah.
do it. So how do you
Get back to
decouple
that.
the, I mean, your model must have been for a fixed ratio starting composition for the metal, but with different
Yeah, we had to.
sulfur and water contents.
You know, this simplified diagram, it's obviously a simplification of, we played different scenarios,
Right.
but what we really tried to do is we said, it looks as though sulfur is really important, so we really highlighted the behavior of sulfur, and we said, all right, let's look at 2 chloride concentrations. So there's many games that you can play with, but we were convinced that sulfur was really important for 2 reasons. For molybdenum, we have a redox. We also modeled redox in this study as well. Molybdenum can be in the 6+ state. It's very mobile in the 6+ state. It's immobile in the 4+ state, and it comes out as a sulfide. I mean, molybdenum and molybdenite is the dominant moly mineral. So sulfur is then going to play a role in precipitation rather than transport in the case of moly. I didn't point out, but if you look at this curve here, you'll notice that kink, which actually corresponds to a kink in the data. That's actually where we changed the FO2 buffer. So above that kink, we're buffering it with anhydrite. Below, we're buffering it with a sulfide. We had to do that, but it's actually interesting that the kink is more or less corresponding to a kink in the data. We're really excited because, you know, this is just metal ratios in an ore deposit, and we're able to kind of model them with this aqueous chemistry. I think you've had enough of me now. Marcus?
It's not totally relevant, but I went to work with Chuquicamata with a bunch of Dalhousie students.
Okay.
And I knew that there was a lot of zinc in Chuquicamata. There's more zinc in many places than copper.
Yep.
But they didn't know. They didn't believe me. So we went there, we started logging the core. I said, this sphalerite. No, that's not sphalerite. They called it something else. And they were really mad at this academics coming. And about 2 weeks later, we were there. There was an explosion at the smelter where they put the copper ore, chalcopyrite and bornite and so on, into vats, and they heat it up. And they're chimneys. And 2 of the chimneys, 2 of the vats exploded and killed 2 miners. And on the chimney, it was clogged with metallic zinc. So they believed us that there was zinc in the new part that they were mining. So anyway, definitely it was carried by vapor.
Yep, yeah.
There's no question. But again, there must have been a lot of sulfur in that vapor.
Yeah, in the case of zinc, my gut feeling, we haven't done experiments with zinc, but my gut feeling would be it would be a chloride complex in the vapor. But yeah, you know, just talking about these porphyry systems, we tend to think, zinc is irrelevant. But in fact, if you actually look at volcanic gases, and we did a fairly detailed study on Merapi volcano in Indonesia, and these gases actually do have significant zinc in them. And we argued that that volcano really represents the top of a porphyry system at depth. Not a new idea. Sillitoe came up with that idea back, I think, in about 1972, that porphyries are really just the bottoms of these systems that have volcanoes sitting on the top. So we actually measured the volcanic gases at the top, and the ratios that we got were actually quite interesting. Sorry, this last little anecdote, we actually looked at melt inclusions in tephra, and we were able to show that the metal ratios in the volcanic gases were exactly the same as in the tephra. And what we saw in the tephra, we actually had magmatic sulfides. We actually had magmatic sulfides coexisting with silicate melt. In other words, your classic sulfide silicate immiscibility. And in fact, the tephra were actually fairly mafic in composition, basaltic in composition. So in that particular volcano, what is actually happening is you have a resident magma chamber, which is dacitic in composition, and about every 5 years, you get a pulse of mafic magma that actually generates the explosion. And you can then go and sample the gases straight after that, and what has happened is we simply transferred the metals from the immiscible sulfide liquid up into the vapor. So I'm not trying to say that zinc is dominant, but there is some zinc. And why wouldn't there be?
Okay, so I'd like to thank Willy for an excellent presentation and also pushing us to ask questions and challenge him on these ideas. And one of the things that we like to give our speakers is a little something to remind you of your visit here. And it's packaged for travel, since I know you have to do a little bit of traveling. And so I'd just like to thank you again for this. So our graduate students are asked to stay here and have lunch with Willy, and you can ask him questions that you may have been afraid to ask in a public setting. And
Undergraduates too.
Oh, and the undergraduates too.
And the rest get kicked out, so we'll just have a little.
Yeah, so you get the speaker without us faculty around to invite him. Okay? So thank you again.